Hey everybody, Mr. Judson here. Hey, just one thing real quick. There's a lot of questions about Central Washington, and I put out the video and also the information email, but I think there's still some questions out there that you guys have. So I'm going to try and do a Teams meeting on Wednesday. Let's see, if school starts at 7:30, so we'll go ahead and do it then. Yeah, right. I know. I hear you guys. You don't even get out of bed until what, noon? 1? All right, let's go Wednesday at 11. That'll give you guys a chance to still sleep in. But those who are signed up for Central Washington Credit and still have some questions, let's do a Teams meeting at 11 o'clock on Wednesday. And I'll send out the invite for you guys. I am not very good at this. I've only done it 4 times, but I did do a math department meeting last week, and it ended up being successful, so we'll go ahead and give that a shot. All right, so Wednesday at 11. All right, so remember our goal when we're simplifying trig expressions is to try and get down to one term, one trig function, and no fractions. It's always what we're trying to shoot for. Doesn't mean it'll always happen, but that's what we're trying to get to. So let's go ahead and try this one. We want to simplify this trig expression. And I'll give you guys a few seconds to attempt that. All right, so for anyone who's staring at this going, I have no idea what to do. Don't forget our number one strategy is if you don't know what to do, change the sines and cosines. We should always make it at least that far. There's no reason why we shouldn't make it at least that far. So if I did that, I would have sine theta plus a cotangent is equal to cosine theta over sine theta times the cosine theta. Think of that as cosine theta over 1. And so if I multiply these two fractions, what I get is sine theta plus cosine squared theta over sine theta. Don't forget, you always have to include your angles in here. The trig function by itself really has no meaning. So one of our strategies was if there are 2 terms and we see fractions, let's consider getting a common denominator and adding those 2 fractions together. So to get a common denominator, I'd want to multiply this one, top and bottom, by sine theta. And so now what I have is a sine squared theta over sine theta plus cosine squared theta over sine theta. I've got the common denominator. I suppose I could have just gone straight to the fraction. Sine squared theta plus cosine squared theta over sine theta. And, again, one of our strategies, every time you see an exponent of 2, think of those Pythagorean identities. And if you guys haven't done this, you should have a list of all those identities kind of sitting beside you while you're doing this. In a normal school year, I would say you want to try and memorize all those. But everything's weird this year, so if you didn't, that's fine. I will still give you guys a test over this chapter, a practice test. And if you sat there with some notes beside you, that's fine. I think the important thing is we understand what we're doing and we can get through it. Those who are taking the Central Washington final, you guys will get a note card to use, and so you should be fine with that. All right, so sine squared plus cosine squared equals 1. That means I've got 1 over the sine theta, which is equal to a cosecant theta. And there it is. We met all 3 of our conditions. Let's try another one. All right, so here we go. We got sine theta over 1 plus cosine theta plus cosine theta over sine theta. If somebody wanted to add an extra step to this, I guess they could have called this a cotangent theta. But we'll leave it like this. So we already have sines and cosines, so that's not really helpful. We need to just figure out where to go from there. You guys go ahead and try it. All right, so again, my first thought is if I want to get down to one term, I'm going to have to add these fractions together. So let's go ahead and do that. So I'll multiply this side by 1 plus cosine theta, top and bottom. Make sure you include those parentheses because that means this cosine has to get distributed to both of those. And again, this is a fraction that's equal to 1. Right? All we're doing is multiplying by 1. We're changing the way it looks, not the value of each fraction. Okay, over here I'll multiply top and bottom by a sine theta. So again, I'm multiplying by 1. So I'm not changing the value, I'm just changing the way that this thing looks. Alright, so now what I get is, this time I'll just go straight to the common denominator. I'm not going to multiply this out just yet because in the back of my mind I'm thinking maybe something will cancel. And so I would have to just turn right around and factor it again. So I'm gonna leave the denominator in factored form. And then in the numerator I'd have a sine squared of theta plus, when I distribute this, I would get a cosine theta and then plus a cosine squared theta. Well, here's that sine squared plus cosine squared again. We know that those two added together would equal 1. So I now have 1 plus cosine theta over sine theta times 1 plus cosine theta. So my assumption was true. Not always, but this time it was. I left it in factored form, and I ended up getting this factor in the numerator. And so that means I can cancel those. Again, we're saying that divided by that equals 1. And so now it looks kind of like the previous problem. I've got 1 over the sine theta, and that's equal to a cosecant theta. There it is. All right, let's try another problem. All right, so this one's slightly different. What they're saying is they want us to write the expression without using fractions. I need to get rid of this fraction. I'm not really trying to meet all three of these. If I do, that's fine, but really my goal is just to get rid of the fraction. Okay? Yeah, if you don't know what to do, change the sines and cosines. Well, that's not very helpful here, is it? We already have that. So this is a new strategy. We want to multiply top and bottom by the conjugate. So if you don't remember what a conjugate is, that's like x plus 2 times x minus 2. These are conjugates of each other. It's the same factor. The only difference is one we're adding, one we're subtracting. Okay? So if I wanted to multiply by the conjugate to try and get rid of this, maybe I'm trying to get this down to just one term instead of two terms, then I could do this, 1 minus sine of x, and I do the same thing to the top, 1 minus sine of x. Remember, this fraction's equal to 1, so we're changing the way it looks, not its value. Okay, so this is just another strategy to consider as you're going through and attempting these problems. You guys go ahead and take this from there and see if you can finish it. All right, so in the numerator I just have 1 minus the sine of x. In the denominator, when I FOIL this, I would get 1 minus a sine of x, and then plus a sine of x. Those will add up to 0, so I just won't even write it down. And then minus sine squared of x. So the moment I see this, I'm now thinking Pythagorean identity. And so I'm going to do my little chicken scratch here. Sine squared plus cosine squared equals 1. I want to see 1 minus a sine squared, so that means I'll move this to the other side and subtract it. So 1 minus a sine squared is equal to a cosine squared. So this now becomes 1 minus sine of x over a cosine squared of x. And remember, my goal here is really just to get rid of the fraction. So if I just, there's actually 3 different ways to do this. If I think of this as 1 over a cosine squared of x times 1 minus sine of x, well then I get a secant squared of x times 1 minus sine of x. No fractions. Okay, I didn't meet all these over here, but the directions didn't ask me to. It didn't say simplify, it says get rid of the fractions. Okay. Another option might have been to say, let's split this into 2 different fractions. So I've got 1 over cosine squared of x minus sine of x. And I'm going to go ahead and write this as cosine of x times cosine of x. Here I'll write this as sine times 1. And this would be a secant squared of x minus sine over cosine would be a tangent of x. And 1 over cosine would be a secant of x. There it is, no fractions. Okay, so both of these would be considered correct answers. I think I've got a third way written down here. Yeah, I could have also taken this and said that's a secant squared of x minus a sine of x, and then 1 over cosine squared would be a secant squared of x. Which really this answer is the same as the first one here. If you distribute that secant squared, you would get this right here. Okay, but again, if you wrote it this way, there's no fractions and you got the job done. Let's try another one. All right, here's another one to try. Same thing. We're just trying to write this expression without using fractions. You guys go ahead and try it. All right. So let's see. I guess I have 2 thoughts. I could go ahead and go straight to sines and cosines, or I could just multiply top and bottom by the conjugate, use that same strategy from the last problem, and then change the sines and cosines afterwards. I think I'm just going to try the conjugate first and I'll see what happens. Okay. I don't know if it's the best method. And that's really important. I get asked this a lot in a normal class. How do you know which way is the best way to go? How do you know how to start? There's no right answer to that. Remember how I said it's kind of like a puzzle? What's the best way to put a puzzle together? Do you start with the pictures that are obvious? Some people like to do the edges all the way around first and then start working on the inside. There's no right or wrong. You just have to pick a way and just go with it. Okay? So I think I'm just going to do the conjugate and see what happens. So this would be a cosecant of x minus 1. Multiply the top by the same thing. And so when I do that, let's see, I get tangent squared of x. Again, I'm not going to multiply this out just yet. Let's just see what happens. And so here I've got a cosecant squared of x then I'll get a negative cosecant, and then a positive cosecant. So those two will add up to 0. And then 1 times negative 1, that's negative 1. So again, that looks kind of like a Pythagorean identity. I see the exponent of 2. And so I'll do my chicken scratch off to the side here. I believe that that one is a cotangent squared plus 1 equals a cosecant squared of x. The reason I'm not just doing c's is because, is it a cosine, is it a cotangent, or is it a cosecant? I don't know which one, so I just wrote it all out. So to get a cosecant of x minus 1, I need to move this 1 over here. So a cotangent squared of x equals cosecant squared of x minus 1. So I'm going to change the denominator to a cotangent squared. So I've got tangent squared of x times cosecant of x minus 1 over a cotangent squared of x. And, really this is 1 over a cotangent squared, and that's really equal to a tangent squared of x. So if you have a trig function, you can move it to the other side of the fraction bar and just change it to its reciprocal function. So a cotangent squared would go up to the numerator and become a tangent squared. If this was a cosine squared, it would go up here and become a secant squared. And if this was a sine squared, it would come up here and be a cosecant squared. Okay, so I'm just going to write this as tangent squared of x times a tangent squared of x times cosecant of x minus 1. And the fraction's gone, so really I'm done. I may want to go ahead and just, call that a tangent to the 4th of x times a cosecant of x minus 1. Now, could this be simplified farther if I change the sines and cosines? Maybe. But they didn't ask me to. All they asked me to do was get rid of the fraction. And we've done that. So I'm going to stop right there. If you think about that, if the goal is to get rid of the fraction, there really are a lot of different possible answers here. We could continue to simplify and stop at any point as long as there aren't any fractions. I think if I change this tangent to sine to the 4th over cosine to the 4th, essentially I just put fractions back into the problem. And so right away I'd go, oh, I don't want to do this. I would just stop right there. Okay. All right, so that's really what we have for today. This isn't that much different than what we did on Thursday. I think we're maybe pushing it a little farther. Maybe the expressions will get a little more complicated. Hey, keep on working this, you guys. I know that this is something that's kind of hard to do. Traditionally, people sort of struggle because the fact that there's different ways to go, a lot of times people don't want to make a decision because they don't want it to be wrong. But you just got to make one and try it and see what happens. If it doesn't work, it doesn't work. Go back and erase and try something else. Okay? All right, so here's our next assignment, number C8, page 380. We're going to do 49 through 67 odd. Hey, another thing that I'm thinking about doing is, a lot of times in college you have what's called office hours, and it's a time where your teacher's available if you have questions. I might pick 1 hour. I'm still thinking about this. I don't know if it's 1 day a week or 2 days a week, but I'll set up 1 hour where I'm available. It'll be like a Teams meeting. I'll send out an invitation, but you don't have to be part of it. I'll title it Office Hours. And if you show up with a question, you guys would join the meeting, and then just go ahead and say, "Hey, Judson, are you there?" And I'll answer. And then if you have questions, that way we can start to get a little bit of interaction. I wish I would have learned all this stuff earlier, but obviously none of us knew this was going to happen. I never really thought I'd be using Teams. I didn't see the point as far as what we were doing in the math class. Now I see the point, you know. So anyway, something that I'm thinking about, and so I'll keep you posted on that. All right. Don't forget Central Washington meeting Wednesday at 11. All right. Talk to you later. Bye.